So now that we've defined our Hamiltonian, let's go ahead and write it out in all of its gory details, because we've buried a lot of stuff here in this del squared operator. So we'll go ahead and expand this out. So again, the Schrodinger equation is h psi equals e psi. So let's go ahead and plug in our h that we have. So we have negative h bar squared over 2 times the mass of the electron times the whole del squared operator in spherical coordinates. So we get 1 over r squared, first derivative with respect to r squared, and I'll go ahead and put the wave function here specifically. So we get the first derivative of the wave function with respect to r, then 1 over r squared sine theta. And in this case, unlike the rigid rotator, the r's are going to stick around. So because r is not fixed in this case, the electron is free to get closer or further away from the nucleus. Derivative with respect to theta, sine theta. And as you can see, I'm looking at my notes. I do not have this memorized. And you don't need to worry about memorizing it either. So d psi d theta plus, we're not done yet, 1 over r squared sine theta, second derivative of the wave function with respect to phi. All right, so that's just the kinetic energy term. So all of that is the del squared operator in 3 dimensions. And then we'll have our potential energy term, which is Coulomb's law, 4 pi epsilon naught r psi. All right, so that's our h psi equals e psi. And this is the equation we need to solve to find our wave functions and our energies for the hydrogen atom. Now you may look at this and think this is one of the problems that we can't solve exactly, but it turns out this is the last one we're going to look at in this class. This is one of the problems we can solve exactly. There are mathematical functions that satisfy this equation. And so let's look a little bit about how we go about doing this. So this is a big mess. We can clean it up a little bit if we multiply both sides by 2me r squared. So this just will simplify things slightly. And the other thing I'm going to do is separate out the r part and the angular part. So the part that depends on r and the parts that depend on theta and phi. So we get negative h bar squared, and this is all the r parts that are left, d dr, r squared, d psi dr. We also have negative h bar squared, and then we'll end up with all their angular parts, 1 over sine theta, d theta, sine theta, d psi d theta. Going to continue on the next line, plus 1 over sine squared theta, second derivative of psi with respect to theta. All right, so that's all in brackets. And then we still have our Coulomb's law, 2me r squared e squared over 4 pi epsilon naught r times psi. And then we'll have our 2me r squared on the energy side of this equation as well. Now, something that may not be obvious, but if we glance at this, we'll see that this part here is the only part with r's in it. Well, not the only part. This part and down here. All right? But these parts don't have any angular dependence. So the parts circled in blue have no theta or phi. And this part here, which extends down to the next line, this part has no r's in it. And so this allows us to use the same technique we've been using for all these problems that we have that have multiple variables, separation of variables. We can look at the r part, the radial part is what we call this, and the angular part separately. And so we can take our wave function and say, well, we can, this depends on 3 variables, right? Our wave functions are going to be dependent on r, theta, and phi. But we can say, well, there will be a part that just depends on r, and there'll be another part we'll call y, because we'll see in a minute, that depends just on theta and phi. So we call this the, oh, let me get my colors right to match. This is called the radial part of the wave function, since it depends on this radius parameter, radius variable. And we have the angular part, because it depends on the two angles that we have defined for our system, theta and phi. And we can solve each of these separately. In fact, the part on the right, the angular part, this is just the exact same as the rigid rotator. If we go back to this equation that I have up here, this part circled in red is the exact same as the derivative that we saw for the rigid rotator. Once we get rid of all the r's, it's just the angles, and that's the same as the rigid rotator. And so it's actually the exact same solutions for the angular part. The solutions are the spherical harmonic functions. All right. And so that's why I use the symbol y, because the solutions are these YLM functions that we looked at a little bit in the last chapter. And in the next video, we'll look a little bit more in more detail at these wave functions and how we can separate these out into its own variables too. The theta and phi separate out as well.